Okay, so now we have described our two forces and we looked at how we determine the magnitude of the electrical force specifically. And so we're ready to kind of put these two forces together. So basically we're going to sum both of the forces and we're going to determine the direction of each of the forces. And if they're in the same direction, we simply add them. But if they're in opposite directions, we're going to have to determine the equilibrium potential and the membrane potential, okay? So if the chemical and electrical forces are in the same direction, so let's say we have a particle that has a higher concentration outside and a lower concentration inside, it has a concentration gradient into the cell. Let's say we also have a particle like sodium that has a higher positive charge outside and this negative environment inside of the cell. And so sodium really wants to get into the cell. So sodium is an example of an ion that has an electrical force into the cell and a chemical force into the cell. And so if we add those two forces together, we get the electrochemical force on sodium, which is going to be very positive because we simply combine those two forces, but it's also going to be very strong in terms of the magnitude. Okay? It's going to really want to get into the cell. Now, if the forces are in different directions, opposite directions, things get a little bit more complicated here. So what we have to do is see which direction is the stronger force in. So we're going to look at the value of those forces and determine, is the stronger force going out of the cell or is the stronger force going into the cell? And then we simply subtract the smaller force from the larger force in terms of determining the size of that force. Okay? All right. Now, let's look at a question here before we move on. So if a chemical gradient exists, right? So we have a high concentration versus low concentration. Which conditions would be needed so that this particle does not move even if the membrane is permeable to the particle? So let's say we have a concentration gradient set up. What would have to happen for this particle to not move? So let me kind of break that down a little bit more. So we know that two forces are acting on this particle, a chemical force and an electrical force. Now, if we have a chemical force that favors movement, what would the electrical force have to look like in order for there to be no movement? Yeah, exactly. So if the forces are equal but opposite, then we would have no movement because the electrical force would completely cancel out the chemical force, okay? An easy way to think about this is a tug of war. So if you have two groups of people on either side of a tug of war, and they both have the exact same strength, the exact same build, the exact same musculature, you're going to have zero movement, right? You have equal and opposite forces, so you have zero movement, okay? All right. So when the electrical force is equal to but opposite of the direction of the chemical force, then we have zero movement of the particle in question. This brings us to the equilibrium potential. Now, the equilibrium potential is a type of membrane potential. So it's a specific value in terms of the membrane potential that exists when the electrical force is exactly equal and opposite to the chemical force. So the particle at question is said to be at equilibrium, meaning it's not moving, okay? Now that is a direct indicator of the chemical driving force, okay? So basically, at this equilibrium potential, the chemical has gotten to equilibrium, so it's no longer moving, okay? So we no longer have a chemical driving force. All right, so let's look at what that looks like here. So if our membrane potential is equal to our equilibrium potential, the membrane potential is indicating what force? Which of our two forces? The membrane potential is an indicator of which of our two forces? The chemical or the electrical? So we said the membrane potential is the separation of charge. So is that chemical or electrical? Electrical. So the membrane potential is an indicator of the electrical driving force. The equilibrium potential is an indicator of which of our two forces? What force would be acting on a particle to bring it to equilibrium, to bring it to equal concentrations on both sides? Is it an electrical force or a concentration gradient? It would be a concentration gradient. So the membrane potential is an indicator of our electrical force. The equilibrium potential is an indicator of our chemical force. And if these two are equal and opposite, then the force is equal to zero, meaning that that particle is not going to move, right? And that's where our equilibrium potential comes in. It's going to help us determine what the concentration gradient is or what the direction of the larger force is. So in this example, we're using specifically the equilibrium potential of potassium. So every ion has its own equilibrium potential, and that's a fixed value. And so for potassium, the equilibrium potential is negative 94 millivolts. And just to break that down further, at negative 94 millivolts, potassium is at equilibrium. It has the exact same concentration inside as outside, so it's not moving. Now, if the membrane potential gets to negative 94, then we also have an electrical force where potassium will not move because the electrical force directly opposes the chemical force. Okay, and that's what we mean by equilibrium potential, the force to bring that particle to zero movement.